Hello, and welcome to the Calculus 3 full review for Purdue University. Probably should have written that. Purdue University. So, in this review, we are going to cover a lot of topics. We're going to cover Lagrange multipliers, a better optimization method compared to what we learned for exam 1. So we're going to be finding the absolute min and max. We're going to be looking at double integrals, rectangular and general forms, polar integrals. We're going to learn how to reverse the bounds for double and triple integrals. And I'm going to teach you average value. We're going to move on to triple integrals, which will be Cartesian / just rectangular, and then cylindrical, and the scariest of all, spherical integrals. And then after that, we're going to take a little break to do integrals and mass calculations. I'm going to teach you about moment in the centroid. The centroid is simply what we call the center of mass in this case. We're going to learn how to do that in 2D and in 3D. Then we're going to do vector fields, potential functions, and scalar vectors, and the gradient vector field, as well as radial vector fields. And then the last one, which is the big topic, is line integrals of all flavors. Circulation, curl, workflow, flux, divergence, Green's theorem, the conservative vector fields, and the fundamental theorem of line integrals. So before we move on to any of that, here are a few fundamental trig identities that I think you should know. If you want, you can take a screenshot right now. There's the one we know all the best, sine squared of theta plus cosine squared of theta equals 1. I'd say that this one's probably the most important to know. It shows up a lot, but all of these have a chance of occurring one or the other way, so I would recommend knowing all of them. After that, this is just some stuff I labeled Greek stuff. You don't actually need to know what any of these things are, but I say everything by the Greek symbols because just used to it. So the gradient symbol, that's the del, lambda, rho, phi, theta, and of course pi. Then last but not least, okay, a little warning about this guide. Not everything is fully comprehensive because I am still taking this class right now as a freshman. But so expect less material as we go on, because I'd like to think that this exam right here, exam 2, really likes to build on itself. So as you get good at the stuff in the start, it really helps you get good at the stuff in the end. So without further ado, let us start. Okay. Lagrange multipliers. So, Lagrange multipliers are an optimization technique for finding the absolute min and absolute mass faster. So, we have this function f right here, which you'll see as f of x, y, z, ... Sometimes it's just f of x, y, but you should know is that it's your starting function. And then you have a constraint g, which will be in the form of g of x, y, z, but it's different because it will be equal to a constant. So these values must lie on a specific curve or surface that is defined by your constraint of g. Okay, so before I get into solving it, you should know this form right here. This is the form that all of these questions will eventually form into, which is that the gradient of the f function will be equal to any constant lambda multiplied by the gradient of the g constraint. So how do you solve these? Well, here are the steps right here. You can take a screenshot. The first step is to identify which is your function f and which is your constraint g. Take the gradient, also known as the partial derivatives, vectors of both of them, then set them equal to each other with g having lambda attached to it. Number 4 is solve the system of equations and plug back into constraint equal to find the critical points. And then the last step is to plug these critical points into function f to find absolute extrema, min, and max. Now, if that was a bit confusing, I also have an example for you. So here's your example, right? f of x is equal to x squared plus 2y squared, which is subject to x squared plus y squared equals 1, and you have to find the min and max. So as you can see, I find my gradients of both first, then I set them equal to each other with lambda attached to constraint g, and then in this case, I find an x, I find a y, so I find out that my x is equal to 0 and my lambda can be equal to 1, so I plug my x back into my constraint to find what my y's can be equal to. Thus, I find my critical points at 0, 1 and 0, negative 1, and then I plug my lambda value back into the y equation to find what my y's can be equal to, and then I plug my y equation back into my x, into the g constraint, in order to find what my x's could be, which gives me my second pair of critical points. Thus, after I plug it back into my original f function, I find that my answers are max of 2 and min of 1 occurring at these points. Another method that we did see in here is to solve for your lambda, equate it, and then solve for x and y, and then plug into your constraint in order to continue the road into finding your critical points. Now, here's some additional details. It may give you a point xyz, and it asks you to find the shortest or the longest distance. The shortest is your min, and the longest is your max. Now, if you want to do that, you're going to have to use the distance formula. This is the distance formula right here. It'll be the second x value minus the first x value squared plus etc. And that will be equal to your f function. Now, then you solve it like normal. And another trick you can do is you can divide. As you can see in this equation right here, I had my functions equal to each other, and I simply divided them to cancel out like terms, and then I went about solving it. If you want to, you can take a screenshot. And then this is an example of the distance in motion. As you can see, closest to this point, I use the distance formula here, and then I go about solving it like normal. So that was Lagrange multipliers. We're going to move on to double integrals, rectangular and general. Sorry, if I ever pause, it's because I'm probably taking a drink of my Monster. It's orange flavored. Okay, so double integrals. This extends our normal single variable integrals, which is the area under a curve, to two variables, which effectively finds you the volume of a solid now. Okay, so this is our form right here. This is our volume. Our volume is this double integral above the region and below z equals f, the function f of x, y. This is our x. As you can see, it's bound between two numbers here, a, b, c, and d. These are for our rectangular double integrals. So how I want you to think about these is, I'll write it down here. Think about it like this, right? It's like you're stacking area slices. That's how I want you to think about it. Okay, so here's something super important to know. When you're taking the double integral over a rectangular region, order doesn't matter. As you can see in this case, x can go from here to this point, y goes from this point to this point. But in a general region, order does matter, because now x can go from this line to this line, and y can go from this line to this line. So when you're taking the double integral over a rectangular region, order doesn't matter, but over a general region, order does matter. Why does it matter? Kind of what I just said right there. The bounds of the inner integral will always be a function of the outer variable. So that's the form right there. And I have two examples. Here's an example for rectangular. Here's an example for general. moving on to reversing, or you could also say reordering the order. So this is a very critical technique for when the original integrand, which are your bounds, and the integrand is going to be just that double integral. You don't have to confuse yourself over that. It's when it can't be easily integrated over what bounds you currently have. So you're going to want to learn these two regions. This is a type 1 region, which means you integrate with respect to y first. You can see it goes down to up, down to up. But if you have a type 2 region, it goes left to right. So when you have a type 1 region, for example, since type 1 and type 2 regions are exclusive to double integrals, a type 1 region will be your dy dx, while your type 2 regions will be your dx dy. Okay, so here are steps. They work both ways. So what I haven't told you guys is that you should learn how to draw these regions. Especially with the double integrals, they will never be too horribly difficult. The triple integrals, you get a pass on not being able to draw them because they do get very tricky for some of them. But for double integrals, learn to draw. Okay, so the first step is to set up your integral first. How I want you to think of it is that in this case, this is actually a type 2 integral. So when you integrate with y, it's just 2 points. When you integrate with x, it's x as a function of y on both of them. So what you want to do is graph the region, extract your bounds, right? Y is bound between c and d, while x is bound between x1 of y and x2 of y. And now you rewrite in terms of the new variables, but it's much better explained with an example. Okay, so you want to reverse the order of a double integral f of xy bounded by x equals y, x equals 1, y equals 1, and the x plane. So we have it written out just right here. This is the original graph. As you can see, it's a type 2 graph, so it goes from left to right in this case, and we want to reverse it to being a type 1 graph. So here it is. Just like this. And then here's an example for a triple integral, which is a little bit more confusing to think of. Okay, and remember, I will also be posting this PDF in the description of this video. I'm not too great at explaining things. I'm good at writing things down, but I'm not too great at explaining. So if you don't like my explanation, which I'm assuming some of y'all will probably not, just download the PDF and study like that. So these are double integrals over polar coordinates. So polar coordinates are the next step for double integrals, since they're the region of integration d of a circle, an annulus sector. Basically anything that in an integral contains something resemblant of x squared plus y squared. So you need to know these. You need to know that x is equal to r cosine of theta, y is equal to r sine of theta, and r squared, which is going to be your radius, is equal to x squared plus y squared. So we have a new change. Remember that we had a dA. The dA area used to be dx dy, but now it's r times dr d theta. And you must remember this r right here. This r is very important. As you can see, it now changes. It's now f of r cosine theta, r sine theta, and again, the r. So here are our new bounds. As you can see, the r bounds are now a function of the theta. And here's a better way to see it. You see, your r is going to be your radius, and your theta is the angle that's swept across this circle. Okay, so here's an example for it. You have this formula. D is bounded by this circle right here. You simply substitute r squared equals x squared plus y squared. You find that it's a full circle, so you have your bounds now, and then you simply reintegrate in. And here's a tip for converting from Cartesian. So if you have your original bounds, if x is greater than or equal to 0, then you know that x must always be a positive value, which means that x can only be from 0 to pi over 2, or if they ask for a semicircle, it could also be from negative pi over 2 to pi over 2. Same with y. If y is less than 0, y can only be between 0 and pi, because that's the only area where y is a positive value. And also, when you're integrating over a double integral, follow the least bounds. Always integrate what has variables in it first and leave the constants last. Okay. Double integrals for average value. Now, average value is a bit easier to understand. Just remember, it's the normal double integral value, except you divide it by the area. So for example, if I had the area of this rectangle here, you know the area in this case is 2 times 5, which is 10. So all you simply do is evaluate the rest of the integral, and at the very end, you multiply by 1 over 10, divide by 10, you simplify, get your answer 5 over 6. That's all average value is just dividing by the area. Okay, we're moving on to triple integrals. Ooh, scary. Okay, rectangular triple integrals. So triple integrals are now the next step to double integrals, and I'd like to say like one of the more final forms of regular integration. So the triple integral is used to integrate a function of 3 variables, f of x, y, z, over a 3D solid, which is now E instead of R. So you should know that the volume of a triple integral should be 1, where the dv is now dx, dy, dz for rectangular. So now it has this form. It goes from a to b for x, c to d for y. And for some reason, mathematicians really like using p and q for z. So that's what we're using. So here's an example for a rectangular right here. This is a bit more simple since your bounds are just constants. So you just set it up like any other integral would and solve it to get 4. And for general, I'm going to teach you a little bit about how to do it. So you want to find the volume of a solid E that lies below this surface right here. This surface is like weird triangle thing. This is called a tetrahedron, but this top surface is it's the top surface and the XYZ plane. So it's also bound by these planes right here. Okay, so what I would first do is, in order to find your bounds, I would have Z equal, and I would find my bounds like this. So you solve the bounds for a floor. So in this case, this would be your floor. This area right here. I'm going to erase that. But that would be your floor. So you have your x bounds right here, your y bounds right here. And then after you find the bounds for your floor, which in this case will be your dy dx, you then build up to finding the rest of your z. So in this case, it was a bit easier. In order to find z, we have this equation already. So if we wanted to find z, we simply just had to set everything else that wasn't z over to the right side. And then once it was set over to z, we just divided by 2. And also, we didn't have to do the floor method for this one. I taught it to you, but you don't have to do the floor method. If you really want to put it into a form of dz, dy, dx. What you can also do is simply, once you find your z, you know it's from 0, so you set 0 equal to your upper z bound, and then just continue that with y, and then continue that with x. And then you simply solve. Okay. Triple integrals, cylindrical. Now, these are actually my favorite ones for triple integrals. Wait, that's a lie. No, I do like spherical. Hold on a second. So they are in the form of r, theta, and z. So they're like polar coordinates, but in the x, y, z plane. So your dv is now r dz dr d theta. That r continues to come back, so remember it. And this is your new form now. So this is what it looks like, right? Your r is your radius. Your theta is still the area swept of the circle, but now you have z, and z is your height, which makes up that cylinder. So here's some fundamental ideas. If you're given two z functions, set them equal to each other. For example, I have this z function and this z. I know that x squared plus y squared is equal to r squared. So if I set r squared and then move the constants over to one side, now I can solve for my radius. And also, you can convert these back into just a regular double integral polar, because if you have two z functions, you can just do z top minus z bottom, and that gets you your f function. In this case, you don't have to do a triple integral, you just have to do a double integral. And remember that theta always runs from 0 to 2 pi. So here's an example. You find the volume of an object of z equals 9 minus x squared minus y squared, and z equals 0. So as you can see, I set z equal to z, found my bounds, and then solved it. Oh, and last tip for cylindrical. Since in most of these questions, there won't be an area where theta gets included. So actually, if you want, at the very start, you can turn this into a double integral by simply already knowing that it's just going to be multiplied by 2 pi in the end, because there will be no thetas that will be integrated. So it'll just be multiplied by 2 pi. As you can see in the end. Okay, so spherical triple integrals. So this is what we like to call the big bad of triple integrals, because it's very scary. These are for spheres, these are for cones, in this case, but they are very scary, and there is a lot of memorization, but they're the most powerful tool for integrating spheres, cones, and just general radial symmetry. So here's stuff you must know. We're now introducing rho into the equation. We're introducing phi, which is this weird symbol that looks like theta, and we still have our good old reliable theta. So you should just know that rho squared is equal to x squared plus y squared plus z squared. You should know that x now equals this, y equals this, z equals this. And these are some more basic derivations that we got from just using trigonometry functions. And here's how you can imagine it, right? Your rho is the distance to an imaginary point P on the cylinder. Sorry, not the cylinder, the sphere. I'm actually going to go for theta first. Theta is still the same. It's just the angle swept in this xy plane. But your phi is the angle between the z-axis. So now we're including the positive z-axis and this line P that we draw in the cylinder. What you should know is that while theta runs from 0 to 2 pi, phi can only run from 0 to pi. Okay, cool. So here's our new form. I was told to emphasize this a lot, but when you have dv, you should know that rho squared, that one thing that you had to add, remember how we had r dr d theta and then r dz dr d theta. Well, in this case, our r is now rho squared sine of phi. Do not forget this. If you forget this, you will get, what the heck? You'll get all your spherical integration problems probably wrong if it's an integration. So this is a very big example that I cannot completely work through here on this video because it would take so much time. But you should know is that the general form of solving these is the hard part is just finding your bounds. It's not too hard to do all the integration, but finding your bounds, setting things equal to each other, converting these Cartesian coordinates to their spherical counterparts is the secret to finding your bounds. And then as soon as you find your bounds, just do some integration and then you got it. Okay. Mass calculations. So mass calculations, now we're using density. Using density, we can solve for mass and the centroid, the center of mass. So here's some must-knows. You have to know what these moments are. So you can read these as mx, my, and this is just mxy. This is the first way that you can solve for the z for the center of mass, but these also go into mxz, myz, and so on and so forth. What you should know is that when you're solving for these, you will be multiplying by the opposite variable. For example, you see this is mx, you're multiplying by y, and you might be wondering, why is that? Well, when you're finding the center of mass, the center of mass are actually equal to these values right here, x bar, y bar, z bar. X bar will be equal to m of y over m. Just like y bar will be equal to m of x over m, z bar will be equal to m of xy over m. But z bar are for the triple mass calculations. And then your simple mass calculation is just a double integral or a triple integral over your density. Okay, so now that we have this is a tip. If you are given a very easy shape, for example, they literally tell you it's a rectangle, you can find the center of mass in a much easier way, because if it's a rectangle, you can just find where the center is, and that's the center of mass. Okay, so here's an example. Find the center of mass, x bar, y bar of a lamina. Don't be scared. A lamina is just some ambiguous shape which occupies the rectangular region, this. So it's rectangular, but it's not a rectangle. For example, I drew it like this. It could literally be anything else that's embodying this rectangular region. So it just looks like this. It could look like this, but it could also look like, I don't want to draw on this, but it could look like that, or something very strange. So you can see, the first step is always to find your mass, and then find your x bar and your y bar using the moments. Once you have your moments, simply divide your moments by the mass, and that will find your center of mass. Okay, vector fields. Vector fields often confuse people, but I think I can put it in a way that's a bit more simple, right? Okay, so I want you to think about this. A vector field is a function that assigns a vector to every single possible point in a space. So that's confusing. It confused me first too, but you should just know these two. This is a 2D vector field. As you can see, it'll be a vector of f of xy, g of xy. It'll be the same for 3D. Now, what is a scalar field versus a vector field? So when you have a scalar field, which is just a normal function right here, as you can see, it'll return you singular points. So it's kind of like a scatter plot. When you have a vector field, now it returns you multiple values in the form of a vector. So for example, if I were to see this vector right here, I would know that it's nothing in the x direction, but it's positive in the y direction. So yeah, here's the vector field. The vector of it, the vector part of it shows the direction, and this is the magnitude. So, okay, let's go into conservative vector fields. So a vector f is conservative if the gradient of a scalar function, if it is the gradient of a scalar function f. This scalar function f is what we will in the future call the potential function. So here's how you'd write it out. So the vector f is equal to values, components p, components q, where p is the partial derivative of this function f at x, and q is the partial derivative of f at y. Remember, in this case, the vector f is just the gradient of f. So here are some examples of some more complex vector fields. You don't have to know all these, especially not these ones that are in the 3D. But here is how you test for conservative. These are for the curl test. So 2D is a lot easier. It's conservative if these specific partial derivatives, the partial derivative of p, the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. If they are equal to each other, so you could also think of it as f and g. I like to think of it as f and g because in this case, f is just this and g is that. I think it's a lot easier than thinking of it as p and q, but you do you. This is an example of it. I have this function. This is our f. This is our g. They both equal to 1, which means this is a conservative vector field. Now, for 3D, it's a bit harder. 3D, well, not harder, more tedious, I'd say. For 3D, it's conservative if and only if the curl is equal to 0. Now, the curl for 3D is this very long cross product. And you can think of it like this, right? I'm going to write it out. It's the partial of y at h, partial of z at g, the partial of x at h, the partial of y at f, whoopsie daisy, and then the partial of x at g minus the partial of y at f. If you get all these numbers and all of these equal out to, and all these are 0, which means the overall curl is 0, then you have a conservative vector field. Now, this will go into the potential function, but we'll go over that when we're talking about line integrals. The last thing I want to go over for vector fields is the radial vector field. So, a radial vector field is basically when all vectors in the vector field point either away or towards the center. So this is the form for it. These questions have shown up once or twice in the exam I've seen, and the correct answer will always be in the form of x, comma, y. And these are some more ways to think about it. Okay, vector fields, the potential function, as well as the fundamental theorem of line integrals. Okay, so now that we know that if we have a function that is if we have a vector field that is conservative, you can find the line integral of f like this. Now, I can try to explain it in this, but it is such a convoluted way to have to explain it without any numbers that I can only go like this. You take the integral, so imagine, if you will, this is my f, this is my g. Or, since you already have p and q, you take the integral of component p with respect to x, and then you add on a constant. After you have your constant, you take the derivative with respect to y, which gets you this. You set all of that equal to your second component, which will be q, then you integrate it to find your g. You integrate all of that to find your g of y constant, and then you substitute it back into your original f of xy function to find the potential. And if you have three variables, you just repeat it with c. So here's an example, right? You have the vector field 2x plus y comma x plus y. So as you can see, the first thing I do is integrate with respect to x, which gets me x squared plus xy plus this constant g of y. Then I take the derivative with respect to y, so this becomes 0, this becomes x, and now I get g prime of y. After that, I set it equal to my g, which is x plus 2y, which cancels out, so I get g prime of y equals 2y. I integrate both sides to get my y squared, and then I just put it all back to get my final potential function. And it also has a constant, but when you go on to the fundamental theorem of line integrals, that constant doesn't exactly become too important. So the fundamental theorem of line integrals, this will probably save your butt many times. This states that if f is conservative and c is a smooth curve, then the line integral is just the potential function at point B, which is the finishing point, minus the potential function at point A. They're basically saying that, for example, if I had, like this curve right here, if you want to find that, all you just need is to find the potential function at this finishing point and at this starting point. That's all you need. So for an example, I'm actually using the exact same potential function here. We know what the potential function is. All I had to do is plug in these 2 points and subtract them to get my answer. It literally makes it so much easier, but it also has the many great requirements of the vector field has to be conservative and c has to be a smooth line. Okay, so line integrals. Here are the basics that you should know. Parameterization. There are many different types, but here are the ones that I thought you should know the most. Here's how to do a line segment parameterization. So that's your start point plus t times the vector of your final point minus your start point. Here's an example of it. Okay? For your circle is always going to be parameterized as r cosine t, comma r sine of t. So for example, that r is your radius, right? If you had a circle radius 5, now it would be r cosine t, r sine of t. That's how you would do that. For an ellipse, it's a cosine t, b sine of t. So now that it's an ellipse, which isn't a perfect circle, it would have your 3 be your a and your 2 is your b. It's those individual radii. And here's what you must remember. Divergence is the gradient multiplied by your vector field f, so it's a dot product, and your curl is your gradient crossed with your f, so it's a cross product. And circulation always relates to curl, just like flux relates to divergence. But I will get into that. Okay, first one, scalar line integrals. So for scalar line integrals, you have this form right here. This is the most simple form you'll see for the line integrals, where ds, it's this integral of the function times ds, where ds is the magnitude of r prime of t. So here are the steps for it. You parameterize to find r of t. You take the derivative of r of t. You find the magnitude of r of t. You plug r of t back into the function of xy, and then you integrate it. So here's an example where I do that. Great. This is a harder example, so if you can do this, you should be in a pretty good spot. Okay, so vector line integrals. So these are for finding circulation, so that's your flow in your work. And you also do this to find flux, but I will go into that later. Flux. Sorry, not flux, flow. also known as circulation and work. So now instead of a function f, it's a vector field f times the tangent ds. So in this case, it becomes this equation where dr is now only r prime of t. It's not the magnitude of r of t, it's r prime of t. And it equals out to this more simplified equation. Now, if it was put in this form, where this circle now means it's a closed simple loop, you can use what's known as one of the 3 fundamental theorems of calculus for Calc 3, which is Green's theorem. This only occurs on a simple closed curve. This is the form for it. Does it look kind of familiar? It should, because it is strangely familiar to curl. Remember, I told you that curl relates to circulation just like flux relates to divergence. This is actually the curl right here. So here's an example for that. And here's an example where I didn't use Green's theorem. Both of these ways are valid ways to solve it, but one of them is going to be easier and one of them is going to be harder. It's just dependent on certain questions. And then flux. Flux is your vector f times the normal line. So flux actually uses divergence. So divergence is kind of just the opposite of curl. I want to say it's the opposite of curl. It's really not, but it kind of is the opposite of curl if you look at it. Curl, if you think of it in terms of f and g, curl is g of x minus f of y, while divergence is f of x plus g of y. So that's how you do flux, but I'll get into this more later. Okay, I have to thank my supplemental instruction leader, Abby Herman, for donating this very good flow chart. But these are how you compute line integrals. As you can see, oh, what the heck? If you want to find your line integral, if it's a scalar function, you just go down this route. If it's a vector field, all of a sudden you have a lot more things to do. You have to find, is it conservative? If it's conservative, then if it's a closed curve, then you just know it's 0. And if it's not a closed curve, you find the potential function and you can use the fundamental line theorem. If it's not conservative and it's a closed curve, you use Green's theorem. Or you can also just use this. If it's not a closed curve, you can only use the original formula for that integration. But if it is a closed curve, you can use either of these. And here's how you parameterize more simply. Okay, so these are more on Green's theorem and radial vector fields. Green's theorem is just like the cross between the gradient and f. This Green's theorem is very similar to Stokes' theorem, which we haven't learned yet, but I put this meme in here because I thought it was... Okay, I didn't think it was very funny, but I thought you might think it was funny. This is just sad. Okay, and then radial vector fields. This is another way to think of radial vector fields. As I showed you, I didn't really help y'all visualize it, but everything's going in, so it's like the gravitational pull of like a star right here, and an explosion. So I don't know, just like a bomb went off or something. That's all I can say for that. Okay, and then here is just some line integral practice. I'm not gonna go over all of these, but if you want, you can take screenshots, or if you're gonna download the PDF, just do it there. But these are some more line integral practice. I hope I went over everything. Has scalar, workflow, fundamental theorem, finding the potential, Green's theorem, and flux. And here are some more general tips. If you're unsure which is the upper bound, which is the lower bound for two functions, you can plug in a point, and whichever function produces a larger number will be your upper. When you're approaching flux right here, you can find the end. If you have an r of t, find the r prime of t, and then all you have to do, find r prime of t, make the x component, which is the f right here. I say x, but it's the f component. Make it negative, and then swap the two. Okay, this is the distance formula. Remember that the dA for Green's theorem should equal to 1. The integral of any closed loop is 0, if and only if it's conservative. Always integrate bounds with only constants last. This really helps me when I'm having to reorder bounds, is thinking of it like this, is that the inner bound is a function of all the other variables that come before it, and just trickles down a little bit. Do not forget your r's, for the love of God, do not forget your r's, or your rho sine theta. Oh, whoa, I got that wrong. Wait, hold on a second. That should be rho sine phi. And learn how to draw. You got this. I believe in you guys. I believe in, do I believe in myself? Yeah, I don't know. But I gotta study some more anyways. But that is the end of this general guide. I hope you found it helpful. I know I went through it pretty fast, but I'll be linking this PDF down in the end anyways, and have a good day. I hope you learned some good math.